Good morning everyone, I'm TJ and today I'm going to demonstrate structural dynamics in a cantilever beam. And this is an application I'm using in my latest course called Digital Twin Technologies for Condition and Structural Health Monitoring. And I'm using a shaker and a sine sweep function to visualize the lowest three eigenmodes of this cantilever beam. And I'm using a high-speed camera to record the mode shapes during excitations. Here you can see what happens when the sine sweep excitation frequency passes through eigenfrequency number 1. Then the corresponding mode shape number 1 will start to oscillate and you will have resonance. Here you see resonances increases until the excitation frequency has passed eigenfrequency number 1. And then there will be no resonance before the excitation frequency coincides with eigenfrequency number 2, 3, 4, and so on. The purpose of this video is to teach you about eigenfrequencies and mode shapes. You have probably used this formula to calculate the eigenfrequency of an oscillating mass hanging in a spring, but you might not be familiar with the term mode shapes and how you can use a mode shape to solve a structural resonance problem. Then I will teach you about why structural resonances cause problems that could be fatigue or other failure modes. And then I will teach you how to validate a virtual or digital twin model, which you might use in order to get extra information about the structural health of a structure. Then I will teach you how to use a sine sweep function for giving structural excitations in order to check for resonance problems. And then how to avoid structural resonance and hence damage, and how to identify damage and defects by modal analysis. So, let's go through the tasks that I will show you in this video. The first one will be to teach you about eigenfrequencies and modes. That means the basics. The first step in performing a dynamic analysis of a structure is to determine the natural frequencies and mode shapes of the structure, with damping neglected usually. Most finite element solvers, they provide a modal analysis solver for undamped systems, but some are also providing solvers for damped systems. That means they can calculate complex modes. The natural frequencies of a structure are the frequencies at which the structure naturally tends to vibrate if it's subjected to the disturbance. That means when you are applying a sine sweep function and the sine sweep is hitting these frequencies, the eigenfrequencies, you will have resonance and hence problems. Then you know that there is a problem. The deformed shape of a structure at a specific natural frequency of vibration is termed its normal mode of vibration. That means its mode shape. And if you have a problem, a structural dynamic problem, the mode shape can give you information about how you can change the structure in order to eliminate or reduce the structural problems. That means fatigue or other failure modes. And there are many other reasons to compute natural frequencies and mode shapes, as I will show you. Before we go on, I would like to mention why it's important to learn about eigenfrequencies and eigenmodes. In the history, there have been made lots of engineering mistakes causing failure due to resonance problems. And the most well-known is obviously the Takahama bridge that wasn't designed for the gust wind loads or frequencies coincident with the eigenmodes of the bridge. But there are also lots of other cases where you have had critical failures in rotating systems like windmills and helicopters. Okay, let's recap the basics. An eigenfrequency is the frequency at which the cantilever beam tend to oscillate. And all structures have almost infinite number of eigenfrequencies. But for this example, we see the three lower eigenfrequencies of the cantilever beam. These are 6.53, 40.9 and 115 Hz. And for each of these eigenfrequencies, there is a corresponding mode shape. And here you see the first mode shape, the second and third mode shape. And what can you learn from this? Well, let's imagine that this is a cantilever beam with some kind of rotating machinery. So let's just animate this mode shape. Here you see the amplitude is at the end of the beam. So you should not put a rotating machinery at the end of the beam rotating at this speed, because then you have met the resonant frequency and you will have resonance problems. And this amplitude will increase and increase depending on the damping. And here, for example, if you have a rotating system located at the middle of this beam, rotating at this speed, 40.9 Hz, you will have a resonance at this frequency. And that could be dangerous. And it's the same with mode shape number 3. If you have a rotating system at this amplitude or that amplitude, rotating at 115 Hz, you would have resonance. And as a designer, you should do everything you can to avoid resonance problems. Then I will show you some analytical methods to calculate eigenfrequencies and mode shapes of a cantilever beam. These are the formulas for calculating the first 3 eigenfrequencies of a cantilever beam. The first number here is an empirical number given for the first 3 eigenfrequencies. Then we have the E modulus, we have the moment of inertia, the mass and the length of the beam, which are all physical properties. And given the numbers for this cantilever beam, which is in aluminum and half meter long, we get 6.53, 40.9 and 115 Hz. You can also calculate analytically the corresponding mode shapes, but usually you use a finite element code for this. I guess many of you have been using these analytical methods to calculate the eigenfrequencies of a cantilever beam. And perhaps you have also been running modal analysis in a FEM solver to animate the mode shapes of these eigenfrequencies. Perhaps you have also been wondering if my simulation results really matches the physical behavior of a cantilever beam or any other structure. And now I'm going to show you how I have been using a sine sweep function and a physical test rig and a high-speed camera to validate the eigenfrequencies and mode shapes of a structure. Here you see my physical test setup. This is a shaker, and with this shaker I can use a sine sweep function that gradually increases the excitation frequency from 5 to 125 Hz, which is spanning all my 3 eigenfrequencies previously calculated analytically. And I'm recording the motion with a high-speed camera that can record up to 1 million frames per second. And here you see my cantilever beam. It has 2 accelerometers, one here at the support and one at the end. And then I have a Brüel test rig, which is connected to my laptop, which is recording the test results. So here I'm using the sine sweep function to put excitations on my cantilever beam, which we have been analyzing. Here are some recorded samples of my physical test. This animation shows mode shape number 1, and when the sine sweep function frequency approaches 6.5 Hz, this oscillating mode will start to resonate. And when the sine sweep frequency increases and approaches 40.9, the second mode shape will start to oscillate, and it will look like this. And you can still see it with your physical eye and validate it that way. However, when you continuously increases the sine sweep frequency and you approaches 115 Hz, you will initiate oscillations of mode shape number 3, and you can't see this with your eye. So this is in fact the first time I have been able to validate that mode shape number 3 on a cantilever beam looks like this. After this test, I plotted the accelerations from the accelerometer located at the end of the cantilever beam. And as you can see, I got resonance at 5.9, 37.3 and 106.8 Hz. If you compare those resonance frequencies with the analytically calculated eigenfrequencies, you can tell that the match is quite good, but in general the resonance frequencies are a bit lower than the calculated eigenfrequencies. And it could be that I didn't model the material properties correctly, but more likely in this example I didn't clamp the beam good enough. So the clamping was not infinite stiff as presumed when you do the analytical calculations. And this is actually something that is important when you do a digital twin. You will always model a digital twin as it was in mint condition. So in this example, the analytical calculations presume that the cantilever beam was in mint condition, no problems with the clamping. But when you do the physical testing, usually these results should match 100% or very close. But after a while, wear and tear could drift those resonance frequencies away from the initial values. And that would indicate that you have a problem with your clamping or some other errors or failure modes that have occurred. So that's the basic idea by using these type of analysis and test results. You will see there will be a deviation between the analytically predicted values and the physical test observed results. And that's a principle which is important when you want to detect problems or any kind of failure modes acting in your real structure. Then I want to give you a brief introduction to sine sweep functions, which are very much used in physical testing. In this course, you will be using sine sweep function in both physical and virtual testing. And I prepared a web application implemented in Python and Streamlit, which you can use to create linear, quadratic, logarithmic, and hyperbolic sine sweeps with constant amplitudes. And with this app, you could, for example, generate one sine sweep between 4 and 8 Hz to initiate resonances at mode number 1 in the cantilever beam. And you could make another sine sweep between 35 to 40 to excite the second mode, or 105 to 110 Hz to excite mode number 3. Or you could simply create a single sine sweep from 4 to 110 Hz. What you must remember is that you need to use a sampling frequency which is high enough. So typically for this range you should use a sampling frequency which is 10 times 8 Hz, that means 80 Hz. And for this one you should use 40 times 10, that means 400 Hz. And for this one 1100 Hz or 1000 Hz. Then you will properly be able to sample these functions which you see here displayed. And this app will also enable you to display or preview the functions before you export it and use it in physical or virtual testing. The next task we're going to do is to simulate the physical test that we did in FEDEM. Then we will use the same sine sweep function to check for resonances. And we will also calculate the amplification factors in FEDEM. And we will also do modal analysis and see how well those results matches the physical tests and analytical calculations. This is my FEDEM model. It consists of one shell structure representing the cantilever beam I tested. And here I've added a lumped mass meshed with solid elements representing the accelerometer that weighs roughly 3.5 grams. In this end I have clamped the beam, and here I've modeled the Kongsberg shaker using a free joint. And this free joint has a prescribed motion in the vertical direction. And this motion is modeled by the sine sweep function generated in my web application. I could also add stiffness in all directions here, but I still have no numbers for those stiffnesses. So this clamping is assumed to be infinite stiff, as in my analytical calculations. However, I've now added the lump mass here, so I presume that my modal analysis will be more accurate than the analytical calculations. Let's have a look at the results. Here you can see mode shape number 1, and the corresponding Eigen frequency is 5.9 Hz, which is spot on compared to the resonance frequency in the physical test. Then we can look at the second mode, and here is the mode shape of mode number 2, which has a frequency of 38.4 Hz, which is also quite accurate. And then we can have a look at the last mode, the mode number 3 in the physical test, and it has this mode shape and the Eigen frequency of 109 Hz roughly, which is also very precise. There are some small deviations which probably causes the additional mass of the wires which are connecting the accelerometer to the test rig. You might have observed that FEDEM is also giving an additional Eigen frequency at 73 Hz. And this Eigen frequency was not observed in the resonances at the physical test. And the reason is simply that the excitation direction was in the vertical direction. And this mode shape is in the horizontal plane. So in the physical test, we couldn't observe this motion. We would have observed it if the excitation was in the horizontal plane. And the analytical calculations did not include this mode shape. And that's one of the benefits with finite element analysis. It captures all the mode shapes. And perhaps in some situations you would have a horizontal excitation, and then we had to consider this mode shape as well. Then I want to show you the dynamic simulation of the physical test. And here you see I've applied sine sweep function, and here you see how the frequency of the sine sweep is linearly increasing from 5 to 7 Hz during 20 seconds. Here you can see some of the results of the dynamic simulation of the physical test I did. First we can have a look at the excitation frequency, the sine sweep between 5 and 7 Hz, which I applied in 20 seconds. And here you see the dynamic response of the excitations on the structure. Although this is only the rigid body part of the displacement, since I haven't performed an inverse CMS transformation of the supernode displacements yet. Here you see a FFT of the displacement of the end tip, that means the accelerometer. And here you can see that we have a resonance at roughly 6 Hz, which is slightly above 5.9 in the physical test. The deviation might be because of the damping in my model, which might be too high or too low, since I didn't include the effect of the wires on this structure. But you can see there is a good match between the physical test and the simulation results. The last thing I want to show you is a really nice FEDEM feature. Here you see I've applied 2 virtual strain gauges at the clamped end of the cantilever beam. And these are located in typical hotspots. And in FEDEM we can simulate and predict the strain time histories in these hotspots in real time. Most FEM solvers, they have to run full FEM analysis for each time step in order to capture the oscillations in stresses for fatigue analysis, for example. Here I can run the simulation and I can output the stresses in these strain gauges continuously in real time. And here you can see that when the cantilever beam reaches resonance at roughly 6 Hz after 12 seconds, we have a maximum von Mises stress at roughly 52 megapascals. And here you see the peak stress is reached. FEDEM also provides an additional feature which is called virtual brittle lacquer. You can paint the FEM model in advance with a virtual brittle lacquer and run a time domain simulation, and then you will calculate the accumulated damage in the surface of the FEM model. And then you will identify the hotspots. And there you can then apply strain gauges, which you use as virtual sensors in a digital twin simulations. And the main benefit with virtual strain gauges is that they are free of charge and you can't damage them as you can do in a real physical environment. The last task on my list is to document and compare the dynamic amplification factors from the physical test and the dynamic FEDEM simulations. However, this will not be shown in this video because this will be a task for my students and they will receive an Excel spreadsheet to do the comparisons. However, I hope you have all learned some more about structural dynamics and how to use a digital twin for structural health monitoring and the possibility to get accurate results. See you soon.